Welcome to a new test and teardown video. This time it's a Danbridge vacuum tube voltmeter type FR31. I think this one is from 1960 or something like that. And there isn't a lot of features or functions in this one, just dB volts. Oh, that is a really big, hefty switch. It sounds really fantastic. We got the switch and that's all there is about it. Of course, we got the DC or AC input, and then we got an output. And it is very, 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 very heavy. And we can see some tubes. And the fun thing is, this power connector is not what you think it is. See, this one is a modern IEC, and it's not, of course, not working in any way. But of course, I got those old special funky connectors that will work with this. How many funny standards did we go through before we came up with this one for more or less the entire world, right? Let's look a little bit on the inside of this Danbridge tube voltmeter. It's really packed with tubes. I did not expect it to be that many, and we got one more in the little box down there. So this is, of course, the attenuator and all the resistors and all that. They want this to be super shielded. And there's a selenium rectifier down there. I think this is for filaments for that first amplifier tube. And then probably the rest is just running on normal AC filament. So we got quite a lot of different tubes. 6 BR8 pentode, and there's another one right there. And then we have this the EF184. This one is also a pentode. No, I'm saying wrong. The 6BR8 is a pentode triode, actually two tubes, two individual tubes in one. So I'm sorry I said that wrong, but all the other tubes, that will be pentodes. And except this one, of course, the OB2 voltage reference tube. And here is a very, very burned down pentode. I think this is the 6 CB6. And the bigger one here is a power pentode 6AU5. I've been trying, as you can see here, to clean a few capacitors and see, can I figure out how old this thing is? And because in some of those capacitors, normally you can find a little date code. And what is this, Q7? What does that mean? No clue. Yeah, it's all Q7 on those. And look at that. Ugh. That is leaked. See, completely popped and leaked. Oh, this is completely nasty. This is how they should look, with this little rubber valve for overpressure release. Instead of blowing up, they just release the overpressure like that, and then it's not a big hazard. So yes, those 3 capacitors, they're definitely gone. This one looking normal, but it's the same. There's then the valve is just a little bit more internal. And other than that, yes, that will be the high voltage rectifier and some resistors for the filter stuff between those different capacitors. I should, of course, open this and look at that. What is going on with this metal nasty? And of course we need to see a little bit more details here on the right side of the unit. That will be the specifications of the transformer. Everything here nicely, neatly explained, and I kind of like that. So we got an individual 6.3 volts, probably good isolated. That would be for the high voltage pentode system, so they can have the filament hanging high up, while all the other filaments, they are low, near ground, right? And then we got the high voltage and yeah, mains input. We got, I kind of like this with the different inputs, and they say the power transformer works from 50 to 1K. How about that? Yes, since this is pretty old, of course everything is flying leads and just hanging around those test points right here, or solder points for this type of design. So this is pre-circuit board. Still can't find any kind of date codes. That is a little bit sad. I'm still playing around with this and trying to clean everything, and look at that. The wires for the mains entry. I bet, oh yes, I was right. Look at that. Is this good? Let's try and have a look. Yes, that is exactly what I was imagining. Yeah, see? So the wire is tinned, and if you tin a wire and then you screw it in like this, then the tin will eventually, it will just slowly move until there is no pressure, and then you have a loose connection. It's probably the same with the other one. Let's try and zoom in a little bit on that one, and let's take my little favorite tweezer for poking around. Now this seems to be, see, when I'm moving here there is no problem. So this one seems to be okay. So is this also tinned? It's not, because it's super tight or anything, but this one was actually, yeah, it's still tinned, but this one was not loose or anything. You need to fix this. Ay. Let's just fix those little faults. If you really need to do something with your wires before you screw them into things, use those little ferrules, they are little metal tube pins. You stick them in and press them. Then you have all your little copper parts in perfect, nice order. Oh, there's another thing. Look at the fuses, and this is just driving me nuts. Those fuses, they are made of some material that just corrode really bad, and they also damage the sockets. See, it's all green and nasty, and all this corrosion, see, it ends up in here. I don't know if you can see this, but it's all green and nasty. This one is okay, but here it's just really bad. Of course I need to clean this really good and careful. The best is actually just to replace this fuse holder. They are super cheap and very easy to replace. Just one little screw, and bada bing bada bum, you have something that is reliable. I think we need to get a few things straight, because I think I said something wrong earlier in the video. This is the input. The green wire goes to a capacitor, alright? So this means input can only be an AC signal. So far so good. So I'm so sorry if I said something wrong there. And then the output, maybe it's possible to see. So the output here goes via a little yellow wire, and that yellow wire goes to a capacitor. So that's also an AC signal. So now we know for sure what is going on. Oh, this is a funny little shield here, right? So we just know we can also use this as an amplifier for very, very weak signals. I cleaned both of the fuses, and now I will try and plug in some new ones, and then I will try and power it up and see if it works. But of course I know half of the capacitors, they are leaked, so I expect a lot of leakage, or I expect a lot of hum or ripple on the high voltage. All this is high voltage capacitors. We can see this from the voltage rating, and this capacitance value here. This is a very, very common value to use on your high voltage rails, on all of this and all the amplifiers around here. And I figured out this is the high voltage fuse, and this is the filament, because this is 4 amp and 0.4 amp, right? So we are ready to do the first power up, but due to all the things with the capacitors and all that, here is what I want to do, is I want to crank up the voltage nice and slowly. So this is 80 volts and it's using 8 watts. And then I wait a little bit and just see we don't get anything that starts flying sky high. 6 watts. So this means my filaments, they are probably going to start. This is 100. Start to see a little bit. 150, and I think we can easily crank it up all the way to 220. So that is where we are now, and it looks like it's warming up real nice. It's using 80 watts. That is quite a lot. I'll turn off the light and have a look. Is everything nice and shiny? So why are we seeing this? I don't have any input, so we definitely have a DC bias or some offsets in the amplifier, so there is definitely something that is not working, and I don't have a schematic. But I am now in the I think this is 1 volt full range. Let's just try and give it 1 volt. Okay, so it is responding to that. Wait, did you hear that? Yeah. And this is now my reaction time. Did you hear it? It said clickety click, and then the needle was jumping, and then I was turning off. Oh, I have to quickly go and get my thermal camera. What you see right there is the selenium rectifier, and it's not supposed to be this one this fast. So I think it's probably that one. So other than that, I don't find anything supposed to be. I mean, this is of course the tube you see, and that will be the 2 resistors right there. So that is perfectly normal. And then I just walk around and check out what is going. Ooh, a tube that is warm. Ooh, big surprise. But none of the capacitors or anything like that. So far I think it's that one. And here is my new, well, just another old rectifier, but this is silicium and not selenium. So there's a big difference how they behave. That was the old one. And by the way, they're quite easy to figure out those. This is 390 volt, and 90 milliamps. And this one is 1 kilovolts. And it handles, I don't know, 12 amps or something like that. And this is pretty good. So, with the new rectifier in, it's now using only 60 watts. And my zero is now getting low. We can see this is ripple on the output. And this is full scale 1 volt. And I put now in 1 volt, 1 kilohertz. So here, look at the 1 kilohertz and the 50 hertz mains. So I need to go and check some capacitors, and I think this is also the reason why we have this one not going down, and that output as well. Here's a very interesting thing. Let's measure the voltage after the rectifier, and this goes to the big capacitor, that one. And this is the DC voltage when everything is nice and warm. Let's go down in AC and see we got 83 volts of AC. So that capacitor there is not doing what it's supposed to do. The silver one there. Alrighty then, let's change that one. Oh, this is a little bit funny. I had to grab this damn thing on the top here to twist it around and get it out. And 25 plus 25, right? And 450. Look at this. More or less the same specifications. See what happened to size. I mean, the volume here is the difference is just huge. But let's try this one and see what happens. So let's just measure the same way on the new capacitor. So here's our DC voltage, and let's look at the AC. About 4 volts. And there's no filters and nothing here. We go from here via capacitors to all the rest of the capacitors. And so they should be more nice and clean here. So now I know this value here is what is fed into the high voltage supply, regulated supply. Now I'll go and measure the voltages deeper into the system. So it's already a lot better. We can still see some ripple and all that. Of course, it's open and unshielded. And look at the amplitude of the output. This is 1 volt RMS input. We are in the 1 volt input here, right? So let's try something funny. Let's try and skip 1 level down, okay? I don't touch the scope at all. I turn off my input, move it down to 0.3. And of course we get more hum because the amplifier now is better connected to the input, right? And let's see, if I go down and down and down, I get more and more hum. And again, it's because it's completely open. So what happens if I put in 0.3 volt RMS? There you have it. The same amplitude. So this could be used as a practical amplifier for all sorts of really low level signals. Use this amplifier and get the output here, and then you can hear or see what you're doing. There's just one little thing I want to try, and that is the bandwidth. So here we go again. Let's put in 1 volt RMS. Get this nice level like that. Let's try and play a little bit with the frequency. So this is 1 kilohertz. Let's go for 10 kilohertz. See, it's exactly the same. You can dial up here. And then let's go for 100 kilohertz again. It's also the same here on this meter. So what is the maximum frequency? 1 megahertz. What the heck? Oh, okay, here we go. 4 megahertz. We can even see the dB here, so this is -3, right? Let's see. More or less, yeah. Yes, it is. And I just did it by eye. Looking at that one, that was pretty cool. Okay, so it's 4 megahertz -3 dB. That is pretty good. So now I can just go and play with the rest of the capacitors, and it's not super interesting for you to look at. I still think it is a pretty useful voltmeter and amplifier for whatever experiments. So thank you very much for watching. See you around. Bye bye.